In the last video, we took a look at the definition of what it meant for two events to be independent. We came up with this interesting modification of the multiplication law for probability. Now, what this tells us is that we can use this blue formula anytime we know that our events are independent. So if I want to compute probability of A and B, and I know my events are independent, I have a simple way to actually do it. However, it's not always the case that I'm going to know whether two events are independent or not. Take a look here at example 1. At any town college, 100 students were randomly surveyed. It was found that out of these 100, 55 own a bike, 30 own a car, 10 students own both. So are the events a student owns a car, or sorry, a student owns a bicycle, let's call that B, and a student owns a car, we'll call that C, are those independent? Does one affect the other? Now, the bad way to answer a question like this is to base it off of your hunches. We will never be basing things off of our hunches here in this class. Instead, we're going to try to understand what this definition up above tells us we can do to help answer a question like this. Notice that this blue formula has two sides to it that should be equal. However, what we're told in the box above is that those two sides will only be equal if the events A and B are independent. So what we can do is try on that formula and see how it fits in our given scenario. Let's take a look at what I mean by that. So I'll state down here that we want to see if the probability of B and C actually equals the probability of B times C. We kind of have a little question mark sitting right above that equal sign. This is how I can test to see if events are independent. I'm going to find the probability of the left thing, find the probability of the right two things, and compare them. And if they match, if the two sides of this equal sign are indeed equal, then I'll say these events are independent. Okay, so let's take a look at each side. What is the probability that a student owns a bike and owns a car? Well, I know there were 100 students to choose from, and I was told that only 10 students own both. On the other side, I know the probability of owning a bike, well, let's see, there were 55 people that owned a bike out of 100, and there were 30 students that owned a car out of the 100. So the question again is, do these two sides actually come out equal? Well, if I look at the decimal representation of each side, on the left I get 0.10, 10%, and on the other side I'm going to get 0.55 times 0.3. Well, if I actually multiply that out, I end up with 0.165. I can see that these sides here are not independent, or they don't match, and so that means that I do not have the blue formula working. And so I can say that B and C are not independent, which means they must be dependent. Okay, great. This is a really easy way to check. What this means is that apparently if somebody owns a car or a bike, it will affect the likelihood that they own the other thing. It's totally, maybe even expected that that could happen, right? You could imagine if you, say, lived on a college campus and you had a bicycle, maybe you rode that into campus, maybe you'd be less likely to own a car. It's possible. Doesn't seem like it's crazy. But again, we never really just go off our hunches. We always are going to be checking this calculation every single time. Let's take a look and see if we can do it again. Example 2. A survey was given to 125 seniors at a particular high school. They were asked what were their plans after high school. The results are as follows. So you can see the breakdown for males and females. And so here's our question. Are the events female, let's maybe mark that with F, and 2-year college, I'm going to mark that with a 2Y, are those independent? Well, you know what you need to check. So again, you can say we need to check, is the probability of F and 2Y equal to the probability of F times the probability of 2Y? And that's a question. We don't know if those two sides are equal. We'd like to see. So can you go ahead and pause the video here and see if you can compute both sides and see if they actually do match and see what conclusion you would reach. When you hit unpause, you'll see me working through the solution. Okay, well here's what I came up with. I can easily see here that I'm selecting out of 125 students. So the chances that I get someone that's female and going to a 2-year college, there are 30 of those individuals. So 30 out of 125. Now, on the other side, probability that I select a female, well that's 75 out of 125. And 2-year college, that's 50 people out of 125. Now if I go ahead and I check what both sides look like as a decimal, I'll see that on the left side, I end up with the number 0.24, and on the other side, I end up with 0.24. These sides are equal, and so I can say that f and 2y are independent. Apparently, if someone is a female, that doesn't make them any more or less likely to go to a 2-year college, and vice versa. If I have someone that goes to a 2-year college, that doesn't make them any more or less likely to be male or female. Okay, so this is the way that I can check for independence every single time. In the next videos, we'll see what happens if we already know that 2 events are independent. How can I use this blue formula to help calculate probabilities involving ands?